If we take that symmetric equation and multiply both sides by the other's denominator, I'm going to get b2 multiplied by x minus a1, and that's equal to b1 y minus a2. And then I'm going to expand this in, so I'm going to have b2x minus a1b2, and that's equal to b1y minus a2b1. And then I'll just bring everything over to one side here. Actually, no, I'm going to move this over to this side and this over to this side, so I'm going to have b2x minus b1y, and then that's going to stay here and this is going to come over, so I'm going to have a1b2 minus a2b1. So this is just some constant, and these are the coefficients. This equation is actually called the Cartesian equation. Also, it can be known as the scalar equation. But this is the Cartesian equation, and I just want to point out quickly here, look where B2 is and what happened to the B1. Look where the B1 is, and notice the sign compared to the B1 and B2 in this form, or even in the parametric form. The B1 is with the x, and the B2 is with the y. Both of these are positives, or at least they've got a plus sign between them. And now when we have the Cartesian equation, now all of a sudden B2, where it was once with the y, is now with the x, and the B1, which was once with the x, is now with the y, and the sign has changed. So I'll let that percolate for a while with you. Another thing I need to point out is the similarity between the direction vector and the gradient. Remember that gradient we know is rise over run, or y step over x step, or delta y over delta x. And the direction vector that we looked at before was AB, or B1, B2. So this is the direction vector, this is the gradient. So notice we've got delta y over delta x here. Here we've got a over b, but this is the x, that's the x component of the direction vector, and this is the y component of the direction vector. Therefore, if we use these values in the gradient formula, then we get m equals b over a. So that is now the gradient using the direction numbers. So from the direction vector, these are called the direction numbers. So we use that in this form. This is the delta y, and this is the delta x. Okay, so that's how we get the idea of gradient. Now if I use the direction vector as b1, b2, then the gradient would then be b2 over b1. So again, here's the delta y, and here's the delta x. Now there's one other thing that we talk about, and that's called the normal. It can be called the normal vector, usually just called the normal, represented by an n, because it's also a vector. So the normal is vector n. Well, what does normal mean? A normal vector, or a normal, that's actually perpendicular to the direction vector. So if we know that the direction vector has direction numbers b1 and b2, that means that the gradient is b2 over b1. Therefore, what would the normal be? Well, the normal, if we know from previous years of work, it's the negative reciprocal of the gradient, so it would be negative b1 over b2. This now is the new delta y for the normal, and this is the new delta x. Notice what happens if I direct your attention, after we talk about this normal, direct your attention all the way back up here to the Cartesian equation. Notice what I pointed out before, that the b2 is now with the x, the b1 is now with the y, with the opposite sign. Interestingly enough, the coefficients of the x and y in the Cartesian equation are actually the direction numbers of the normal. So the normal vector could be written, sorry, actually that shouldn't have a vector sign on it right here, I apologize for that. That's just the normal, or the perpendicular to this gradient. The normal vector would be b2 negative b1, because the delta y goes with the y component of the normal, and the delta x is with the x component. So the coefficients of x and y in the Cartesian equation are the direction numbers for the normal vector. We'll look at some examples of this tomorrow in class, and we'll look at other examples of vector and parametric equations that we'll study here. One last little thing. We have the direction numbers and the parametric equations, vector equations, etc., symmetric equation, all in 2 dimensions, but all of this can be extended one more dimension to 3 dimensions, and all the same things apply. So if we have some position vector that equals the position vector of a specific point plus t times some direction vector, which can be written as vector r is vector r naught plus t vector d, which then can be written as x, y, z equals x naught, y naught, z naught plus t b1, b2, b3. So r is the position vector of any general point of the line, same as x, y, z. Vector r naught is the position vector of any specific point on the line, just like x naught, y naught, z naught here. D is the direction vector of the line with direction numbers b1, b2, and b3, and of course t is the parameter again. Here's the vector equation in 3 space, and then we can rewrite this into the 3 parametric equations in 3 space. So those are the parametric equations. And we could also rearrange each of these for t. To get the symmetric equation, we'd get x minus x naught all over b1 equals y minus y naught all over b2 equals z minus z naught all over b3. And those all equal t if we care about that. So that's the symmetric equation in 3 dimensions. One thing that we don't have in 3 dimensions is a Cartesian equation of a line, because in 3 dimensions, when we rearrange this and we get a Cartesian equation, the Cartesian equation is actually a plane. Like a plane in space, not an airplane flying through the air. So this could have the Cartesian plane equation ax plus by plus cz plus d equals 0. That would be the Cartesian equation of a plane in space, but this is beyond the scope of our course. So we won't be studying that this year. So those are all the basics of lines in 2 dimensions and 3 dimensions. And we got the parametric, the vector, the Cartesian, and the symmetric. We know how the direction numbers fit in with gradient and how that translates into the normal vector and a perpendicular vector to the gradient. And tomorrow we're going to be looking at some examples in class. Please take a look at the examples in the textbook. Peruse these few practice questions tonight, just so you kind of see what's going to be in store for you for tomorrow. And then we'll be all set to launch into 13C the following day. So thanks for watching, and we'll see you in class.